Hi everyone, and hope you're all fine. So let's carry on with the topic that we started in the previous lecture, which is about process scheduling. In this lecture, I'm going to introduce four more algorithms and wrap up this topic. But first of all, what we did last week. In the previous session, we discussed about CPU scheduling, and I said that we need to have a scheduler in our operating system that can give CPU time to different processes to be able to run multiple programs. So CPU scheduling is the basis of multi-program operating systems. By switching the CPU among processes, the operating system can make the computer more productive. So the scheduler job is to give CPU time to different processes to be able to run multiple programs. Here, in this series of lectures, we discuss only machines with having only one processor. Having multiple cores or multiple processes, the story is different. It's more advanced, which is out of the scope of this unit. Here, in a single processor system, only one process can run at a time. Other must wait until the CPU is free and can be rescheduled. The objective of multiprogramming is to have some process running at all times to maximize CPU utilization. It means that at each time, CPU can run only one process and others should go to the wait queue in different ways using different algorithms. But we want to keep the CPU busy. We don't want to have idle CPU because it's not good in terms of efficiency of the machine. A process is executed until it must wait, typically for the completion of some input-output request. So we have a ready queue. Processes are created. They go to the ready queue. We discussed that before. And then at each time, the operating system and scheduler should give one of these processes CPU time to be executed and others should wait. So the process which is executed in the CPU should again be completed in terms of the execution and be terminated, or it should wait for something. It should require the completion of an event, so it goes to the wait queue. So that's a process. As I said, we have this cycle of CPU, input, output, and wait time and process time. Several processes are kept in the memory at one time. When one process has to wait, the operating system takes the CPU away from that process and gives the CPU to another process. So we have only wait status for the process or running process. So when some processes are running, so CPU works on that and the other goes to waiting process. So, and I said that we have 5 criteria for different algorithms because this scheduling, this timetabling between the processes can be done in different ways. But which one is the best? It depends on some criteria. CPU utilization, we've got to keep the CPU. We want to maximize that. Throughput, the number of processes that complete their execution per unit of time, we want to maximize the throughput. We want to minimum the turnaround time, the amount of time to execute a particular process, the time that they are in the ready queue and be executed, we want to bring it down. Waiting time, we definitely want to minimize the waiting time for each process in the queue. And response time, which should be minimum, which is the amount of time it takes from when a request was submitted until the first response is produced, not output, for time sharing environment. So we have these 5 criteria, and we want to minimize 3 of them and maximize 2 of them. Based on that, we have, at this stage, at this level, we have 6 algorithms. I explained how first come, first serve works, FCFS, we discussed in week 9. Shortest job first in 2 ways, preemptive and non-preemptive, we discussed in week 9, and I said that preemptive short job first is one of the most efficient algorithms that we have for scheduling. Today, I'm going to give explanation about priority scheduling, round-robin scheduling, multi-level queue scheduling, and multi-level feedback queue scheduling. I'll give numerical example for these two, but just explain how these two works. So let's start with priority. A priority scheduling works based on the priority numbers because processes are created and they should get some time to be executed. How that happens? Based on some priority that they get. At the beginning, when they are created, they are attached with a priority number. It's an integer number and shows the priority of that process. CPU, when the operating system sees these processes, try to take the process with the highest priority and gives the CPU time to that process with the higher priority. So the CPU is allocated to process with the highest priority. Smallest integer shows the highest priority. That's important. When you have process with priority 1, 2, 3, 4, it means that the one who's got 1 is the first process should be executed. Shortest job first is the priority scheduling algorithm where priority is the inverse of predicted next CPU burst time. That's right, because in the shortest job first, we look at the burst time and the one who's got the lowest burst time, we wanted to execute that first. It means that we gave priority to that process. Exactly the same as the priority. But in that case, when in the SJF, when we look at the burst time and it was very low, we gave them the higher priority. So priority scheduling works based on this concept. So priority scheduling and SJF, from one point, they are quite similar to each other because they try to prioritize the processes. Again, similar to SJF, we have two approaches for priority scheduling. One of them is preemptive and non-preemptive. As I said, for non-preemptive, we cannot stop any process to be executed. So when a CPU gets a process, it should continue till finish it. No one can stop the CPU. No one can actually disconnect, let's say, the processing this. So CPU gets that process and should execute that to the end of that. But in the preemptive, it's not like that. When a CPU is allocated, when a process is allocated to the CPU, and CPU is running that, is executing that, as soon as another process comes with the higher priority, the CPU should preempt the previous one, the one that was currently running, should actually put in the waiting queue and gets the new process with the higher priority. So it means that the CPU can stop processes from executing and gives the CPU time to the other processes with higher priority. So this is preemptive priority scheduling algorithm, which preempt the CPU if the priority of the newly arrived process is higher than the priority of the currently running process. So let me give you an example for that. Priority scheduling, we've got 5 processes, we've got the burst time for them, and we've got the priority. All of them arrive at the time 0. It means that when we are here, I want to create this Gantt chart and explain you how it works. So all of them arrive here. At this time 0, I have 5 processes, P1 till P5. This is the priority non-preemptive scheduling algorithm. It means that we've got to pick the process with the highest priority. There you go. P2 has got the highest priority. P2 has got the highest priority. The priority is 1. The burst time is 1. So CPU, first of all, gets that. The scheduler actually gives P2 the CPU time. There you go. P2 is here. 1 second, it runs it for 1 second. So we don't have P2 anymore. Let's pick another process with the highest priority. Between 3, 4, 5, 2. 2 has got the highest priority. P5 gets CPU time. There you go, P5, because the priority is 2. For how long? 5 milliseconds. From 1 till 6, 5 milliseconds. Next one, we have 3, 4, 5. 3 has got the highest priority. P1, burst time 10. There you go. P1, 10 milliseconds from 6 till 16. That's it. Next one, 4 and 5. We've got to go for 4 because it's got the highest priority. The CPU time is, the burst time is 2. 2, 16 till 18, P3. And at the end, we've got P4, which the priority is 5, and the burst time is 1, from 18 till 19. So as you see, we only looked at the priority, and based on these numbers, we allocated CPU to them. And this is the Gantt chart that we have, from 0 till 19. Very easy, so we created the Gantt chart. But we've got to calculate always the turnaround time and waiting time for them. Similar to what we did before. First of all, you need always to create this Gantt chart. Based on this Gantt chart, create this table. You've got the burst time from here, you put it in this column, priority from here, put it in this column, and you've got exit time. You get it from here, from your Gantt chart. So P1, the exit time is here. P1, the exit time is 16. P1, exit time is 16. Then you've got to go for P2. P2, exit time is 1. There you go. P3 is 18. P3 is 18. P4 is 19. P5 is 6. These are the exit times. There you go. We've got them. Turnaround time, I explained that. Turnaround time is exit time minus arrival time. So exit time minus arrival time. Exit time, arrival time of all of them is 0. So you've got to subtract this by 0. You get the same numbers for turnaround time. Waiting time is the turnaround time minus the burst time. You subtract these two columns. 16 minus 10, 6. 1 minus 1, 0. And the rest, 16, 18, and 1. That's right. Why? Because here, 16 minus 10 is 6. This is for P1. Look guys, P1 starts from here. It starts at 6. So it's got to wait 6 seconds, 6 milliseconds. So waiting time is 6. So we can easily get the waiting times for all the processes. What is important? Average waiting time. How to find that? Add all these values. 6 plus 0 plus 16 plus 18 plus 1. Add them, divide by 5 is 8.2 milliseconds. So that was the priority. I've solved the problem with priority scheduling algorithm for non-preemptive. Actually, because all the processes arrived at 0, we didn't need to think about preemption because all of them arrived in one point. But let's look at another problem, a very good one. Then we have different arrival time and subsequently we have preemption. So what's that? We've got 5 processes. These are the arrival time. As you see here, 1, 2, 3, 4, 5. The arrival time is 0, 1, 2, 3, 4, 5. As you see, we start at 0, 1, 2, 3, 4, 5. We've got their burst time, and the priority. So at point 0, the priority that the process that we have at point 0 is only P1. There is no other option for P1. So we've got to execute P1. So P1 gets the CPU time and is being executed. It goes for 1 second until P2 arrives. So now at this point we've got to look at that. So the burst time is 9 for P1. It gets 1 second. The remaining is 8, as you see here. This is my remaining 8 milliseconds. Now we have P1 and P2. Now we've got to look at the priority because we have only 2 processes. So which one should be considered? P1 and P2. The priority of P2 is 3. The priority of P1 is 5. So we've got to give CPU time to the P2 because it's got the highest priority. There you go. P2 comes. P2 comes. The burst time is 4. It runs the CPU, execute that for 1 second because we've got to look at that. P3 is coming. So from burst time from 4 turns to 3 because we have 1 second. Now we've got to look at that. Now we have 3 processes. 1, 2, 3. We've got to see which one's got the highest priority, preempt that, and gives that gives the CPU time to that process with the highest priority. Between P1 and P2, P3, as you see, we have these three priorities. Definitely one has got the highest priority. What is the burst time? 5. We don't need to think about that because no one can beat that process because it's got the highest priority. There you go. You've got to get CPU to P3 and run it for 5 milliseconds. There you go. 5 milliseconds and the execution happens and remaining is 0. We don't have any more P3 because it's already been executed. Now from this point, I have all the processes here, as you see the remaining time of all of them, and also I have the priority of them. So it's similar to what we had before because all of them are already arrived. There is no need to preempt any other processes which are being running. So here, this one has been executed. Next one is this one, P4, because the priority is 2. It's the highest priority here. How long? 7. No one can beat that. So we've got to give the CPU to P4. Run it for 7 milliseconds and the remaining is 0. Among these three now, 8, 3, 3, the priorities are 5, 3, and 4. Which one gets the CPU time? This one, because that's a higher priority. P2. P2 gets that and you should run it for 3 seconds. 3 milliseconds, sorry. So there you go, 14 till 17. Next one. Look at the priority between these two. 4 and 5, definitely P5. P5 for 3 seconds, remaining is 0. The last one is P1, which the priority is 5 for 8 seconds. There you go. This is the last step, and you can create your Gantt chart using the priority preemptive algorithm. You can watch that again and again and see how I gave the CPU to different processes based on the priority that they had. So we created the Gantt chart. Let's move on and find the average and turnaround time. So there you go, guys. This is the Gantt chart, and I'll read from this Gantt chart and populate this table. I've got these 3 columns: arrival time, burst time, and priority, and I can read the exit time from here. P1. Exit time is here, guys. I have P1 here, but it hasn't finished here. P1 executed and finished at 28. P2, 17. P3, 7. P4, 14. P5, 20. You've got to, for turnaround time, you've got to subtract these exit time from the arrival. So 0, 1, 2, 3, 4 are the arrival time that you can subtract from this column. It gives you turnaround time. There you go. For waiting time, you've got to subtract this column from the burst time. 28 minus 9, 19. 16 minus 4, 12. 5 minus 5, 0. And for example, look at P3. The waiting time is 3. Let's look at that. P3 arrived here, immediately got the CPU and got executed. It means that it didn't wait anything here. Another one, let's go for P4. P4 is here, executed at 7. It arrived at when? At 3. So it waited 4 seconds. As you see, we can use this column for waiting time. If you added all of these numbers and divided by the number of the processes that you have, 19 plus 12 plus 0 plus 4 plus 13 divided by 5 gives you the average waiting time. You can easily calculate the average turnaround time as well. So, 2 numerical examples, preemptive and non-preemptive priority scheduling algorithm. Just one more thing about the priority scheduling. So, we've got one big problem with priority scheduling algorithm. What is the problem? The problem is called starvation or indefinite blocking. What's that? A process that is ready to run but waiting for the CPU can be considered block. A priority scheduling algorithm can leave some low priority processes waiting indefinitely. In a heavy loaded computer system, a steady stream of higher priority processes can prevent a lower priority process from ever getting the CPU. That's right. Look guys, imagine that you have a big program with loads of processes. Some of the processes, the priority of them, the number that they get for priority is quite big. It means that they are very low priority processes. So when the process comes, the other process comes, because they have a higher priority, they get CPU and be executed. But those lower priority stay at the end of the queue and never get CPU time. We call it a starvation. Some of the processes are starving there. How we can solve this problem? We solve this problem by aging approach. What is aging approach? Aging involves gradually increase the priority of a process that wait in the system for a long time. For example, if priorities range from 1 to 7 low to 0 very high, we can increase the priority of a waiting process by 1 every 15 minutes. What it means? You have a low priority queue. Every 15 minutes, you increase their priority by 1. So it means that they don't stay in the ready queue for forever, because gradually we are increasing their priority and bring them up to the place that they can get CPU time and be executed. So starvation is a problem with the priority, and aging for increasing the priority gradually is an approach that we can solve this problem. So the next one is round robin schedule algorithm that I'll explain that in the next video.